Hello everyone, welcome back. Today we are going to derive the RANS equations for the compressible flows. In the last class we derived the RANS equation for the incompressible flow, and we saw that one term which is basically very different from the Navier-Stokes equation that we see in the mean flow equation is the presence of the Reynolds stress, that is given by rho u prime v prime bar, right. So, we had discussed that now the stress can be written as the summation of both the viscous stress, which is mu del u bar by del y, and then there is a turbulent stress which is given by minus rho u prime v prime bar. So, let us discuss a little bit more about this Reynolds stress before we go to the compressible RANS equations. Okay. So, if you have, let us say, like we have been doing, this is your shear flow, right. So, this is how your shear is, correct. So, if you take about the laminar flow, right. So, your molecules are not jumping, they are all into streamline and going together, right, but they are not jumping from one layer to another layer. But the way your turbulent flow varies from the laminar flow is because you not only have the mean flow motion, which is the bulk motion of the flow, but also there are eddies which basically contributes to the stresses. So, apart from this we have some small eddies, big eddies, okay, which are basically also contributing to stresses. So, you can basically, if you take a typical fluid element, let us say you take the element here, okay, somewhere here or maybe somewhere here, okay. So, if I blow this up, so this is my fluid element, right, and this is how it cutting like this. So, you have a gradient, velocity gradient, because this is a simple shear flow, you have this del u bar by del y, right. So, this is del u bar by del y, right. So, that gives you a stress, right, mu del u bar by del y. So, this will be tau equal to mu del u bar by del y, right. Now, because of the eddies, so if you take at the same fluid element, okay, you have velocity, higher velocity there and low velocity below, but you have a basically motion of certain eddy. Okay. So, these eddies you can consider them as very close to the motion of the molecules. Okay. You can think about the Brownian motion, only that it is not random as the Brownian motion, it is correlated, as you have seen that u prime v prime bar is basically not 0, right. So, this is this eddy is contributing additional stress to this flow, and that can be given by minus rho u prime v prime bar, which is basically a statistical measure. To understand it further, let us take 3 layers maybe from this flow. Okay. So, we have a layer on the top which is moving at the highest speed, and then you have a medium speed and the slowest speed. Okay. And the 3 layer I have taken, right, and then you have this, we are talking about the u prime v prime. So, let us say you have the velocity fluctuation motion on the up direction, right. So, this is v prime. Okay. So, let us say there is a molecule which jumps from the central line to a line which is on this side, right. So, what it will do? So, this will basically take take the momentum from this to the upper layer, and because this is slower at the bottom one. So, it will basically make the it will take the momentum from this layer to the top layer, right. So, it is a momentum transfer from the middle layer to the top layer, and because the middle layer is slower than the top layer. So, the net rate of momentum transfer. So, what will happen is that my u prime will become 0 in this case, right, because it is jumping from the slower layer to the faster layer, right, and it is, that is why it is taking the momentum from the middle layer to the top layer, and your v prime is greater than 0, right, it jumped from this point to another point here, right. So, the v prime is greater than 0. So, you have like u prime v prime is less than 0, and if you take a statistical measure not only for one molecule, but for several molecules, okay, it will become u prime v prime bar, right. Now, think of a molecule which is, let us say, from this layer and it jumps to the bottom layer, right. Now, it has got the higher momentum at the middle layer and it will take that momentum to the bottom layer. So, your u prime will become greater than 0, but now in this case your v prime is less than 0, right, because it is coming from the top to the bottom, right, sorry, middle to the bottom. So, in this case also your u prime v prime bar will become less than 0. Okay. So, in other words, it is like you can define the stress equivalent to the stress, the viscosity that you have. This is called the Reynolds stress, or also called the turbulent stress, okay, which is given by minus rho u prime v prime bar. Okay. Many people also like it as write it as a u prime v prime bar, but this will not be dynamically consistent, I mean dimensionally consistent. So, you can call it as a kinematic Reynolds stress if you want to call it. Okay. Or you can use this minus rho u prime v prime bar, which is the turbulent stress, right. So, if let us say the motion were isotropic, you might have heard about this homogeneous isotropic turbulence, right. So, homogeneous means it is invariant in translation. So, if you have some value here and if you go to another place in the translation, it will remain invariant. So, this is called homogeneous. Okay. And if it is rotational invariant, okay, let us say this is your x y z axis, okay, and let us say you have some value u prime or v prime or w prime, and you go to another axis which is x prime, y prime, z prime, and if the value do not change, then it is called isotropic, right. So, these are homogeneous isotropic turbulence cases. Of course, it cannot happen if there is a wall there, right, because there is a motion on the walls, it will impart some direction, right, directionality. So, it cannot remain isotropic, but for a general flow which is made, let us say the turbulence in a box with all periodic boundary conditions, you can have an isotropic turbulence. In fact, this assumption helps us in our viscosity model, we will discuss that later, right. So, if the turbulence is isotropic, then you can think of a motion where it is like middle layer is slow and both top and bottom layer are basically going faster, right. So, in that case what will happen is that if a molecule jumps from here to here, okay, so that will become u prime v prime negative. On the other hand, if it goes from here to here, in this case your v prime is also negative and u prime also negative, because it is coming from slower layer to the faster layer. So, in this case u prime v prime becomes positive, right. So, the top is negative, bottom is positive. So, in this case if you take the statistical mean of all this u prime v prime, so you will see that it will keep on cancelling out, and in this case you will have u prime v prime bar is equal to 0 or equivalent to 0, I mean it will go approximately to 0. So, in the case of isotropic turbulence, what stresses will matter is the stresses which are there in your diagonal, right, which is basically minus rho u prime bar square minus rho u v prime square minus rho w prime square, right, and so on and so forth. On these terms which are basically deviatoric, they are not isotropic, they will go to 0. Right. So, to repeat it, so the Reynolds stress is a stress like term, okay, which is developing due to the motion of the eddies, okay, or the motion of the fluctuations. The molecules jump from one layer to another layer, they transport the momentum, okay, in the sense of fluctuations, and that generates another stress apart from the mean stress that you get from the viscous forces, right. And as we discussed in the last class, that this term needs to be modeled, because this is if you try to solve the RANS equations. So, you have let us say in incompressible flow you have 4 equations, one mass conservation and 3 momentum conservation in a 3D flow, but you have 10 variables. So, what are the 10 variables you have? We have discussed last time. In the incompressible flow you have u, v, w and p, these are the mean flow variables. You can write it u bar, v bar, w bar and p bar, because they are mean flow. But then you also have minus rho u prime square bar minus rho v prime by square bar minus rho w prime square bar, and then these are the isotropic terms, and then we will have minus rho u prime v prime bar minus rho u prime w prime bar minus rho v prime w prime bar. Okay, these are the deviatoric term. So, these 6 unknowns, you have no information about these 6 unknowns which appear in your momentum equation, right. So, we have to do something about that, we need to model it somehow if you want to solve the problem, and this is what is called a closure problem, that you have more unknowns than the equations. So, how to close this, right. So, let us before you go to the close this problem, let us look at the compressible RANS equations, and whether we have the same issue, the issues become more critical, more detailed, or basically you get rid of that issue. So, let us look at the compressible RANS. Okay, so I am just revising. So, we had seen these equations, we have what difference we have compared to the incompressible flow is that now you do not have the del dot u equal to 0, the divergence is not 0, but you have this entire mass conservation. Okay, del rho by del t plus del by del xi rho ui. Okay, this is mass conservation because the density is also varying. Okay, in the momentum equation, you have this, you can write it as a total derivative, or you can write it in this way. Here in the tau ij, you have basically the deviatoric component as well. Okay, and then you have additional energy equation, right, which is shown here. So, you can write in a thermal energy or total energy. What I am showing here is the total energy equation. This is the total energy where E can be given as E plus P by rho. Okay. So, this is your internal energy, and this is the pressure energy, right, and then you have this enthalpy, which is no, this is E plus, so E is just E plus K. Okay. So, internal energy, which is CVT plus half ui square, right, and then H will be E plus P by rho, right. So, that is basically we are including the pressure term also here, the pressure work is included in this particular term, right, and then you have this stress term and the thermal conductivity term, right. So, yeah, this is what I was saying, that CVT and E plus P by rho, and this is the term that you are saying appearing in the compressible flow equations, because we no longer have del dot equal to 0, right. So, this is not 0. So, they have this additional term appearing, and of course, you will have this thermal conductivity term in the energy equation, right. And this can also be written, you can bring all of them like the pressure term, if you bring on the left hand side, the stress term, viscous stress term, if you bring on the left hand side, you can write everything on the LHS and make it equal to 0. Similarly, on the in the energy equation, you can take the pressure on the left hand side, pressure work on the left hand side, the stress term on the left hand side, thermal conductivity term on the left hand side, and this is how your equation will look like. Okay, this is just writing in a more compact form, and this entire thing can be given a name as Sij star, right. So, this is your Sij, the symmetric stress tensor. So, if you include this minus 1 by 3 del u by del x q also, then it become Sij star, right. This is happening in the compressible flow because del u by del x k is not equal to 0, right. So, we have already derived these equations and seen them, right. Now, comes the problem of averaging, right. So, as we had discussed earlier, that we need to basically average the equations, right. So, because we are solving for the average flow and not the instantaneous flow. If you want to solve the instantaneous flow, we have to use the Navier-Stokes equation, which will be very expensive, and we just cannot solve them, right. So, let us average the equation, follow the procedure that we had earlier, right. So, we had recall the time averaging procedure or the Reynolds averaging procedure. So, we had defined this let us say u bar will be limit t tends to infinity 1 by t, and then integrate t equal to t plus t u x t dt, right. This was the definition that we had, and we had said that this is equivalent to ensemble averaging also. Okay, either equivalent or at least assume that it is equivalent, right. So, whether you have data from the experiment taken done many times and taken average from that, or if you have taken an average in time, and let us say in your CFD simulation, both are equivalent, right. So, how we did last time, we said that okay, my u is equal to u bar plus u prime, and we could say that we said that u prime bar was equal to 0, and then we had got the incompressible lens equation, which was nothing but del dot u bar equal to 0. This was incompressible, okay, and plus del by del t rho ui plus del by del xa rho ui uj. Okay, let me use the bar here. Okay, so I am not using anything on rho because in the compressible flow, right, and then it was del by del xa tau ij bar minus rho ui prime uj prime bar, right, and plus minus del p bar by del xi, right. This we have done, okay, by just doing the averaging. Just try doing that, but remember in the compressible flow rho is not constant, so you cannot take the rho out, okay. So you need to assume that. Okay, so let us take this term for example in the compressible flow. The compressible flow you will have del by del xj rho ui uj, right. To take it let us in x and y direction. So you have this rho uv, okay, and use the same assumption u equal to u bar plus u prime. So now you will have rho is equal to rho bar plus rho prime, okay, and we will also have v equal to v bar plus v prime, okay. Use all these three, okay. Then you can write it rho is equal to rho bar plus rho prime, u is equal to u bar plus u prime, and v equal to v bar plus v prime, okay. Let us work this out, rho bar plus rho prime, and this will become u bar v bar plus u bar v prime plus u prime v bar plus u prime v prime, right. Multiply it again, this is rho bar u bar v bar plus rho bar u bar v prime plus rho bar u prime v bar plus rho bar u prime v prime, okay, and then plus I multiplied rho with all of them. Now I multiply rho prime with all of them. So rho prime u bar v bar plus rho prime u bar v prime plus rho prime u prime v bar and plus rho prime u prime v prime, right. And then as we did earlier, we need to take a average of this entire thing, right. So take the average of this entire thing, top and bottom, right. What will happen now? What are the terms that will get cancelled? So this, as we told that if you take an average, this has become a coefficient, right. So you can take it out of the averaging process anyway, right. So you can write it as rho bar u bar v bar, this term gets retained here, these two term will come out, but then we will have u v prime bar which will go to 0, right. So this term will go to 0. Similarly in this one u prime bar go to 0, okay. Here it will not go to 0 because this is correlation, right. Similarly you will have this term go to 0 because this is rho prime u prime u bar v bar. So what are the terms that remain here? This will not go to 0 because rho prime v prime, there will be correlation between the two, rho prime u prime correlation between the two, and then you have triple correlation. So ultimately the equation will be rho bar u bar v bar plus rho bar u prime v prime bar plus rho prime v prime bar u bar plus rho prime u prime bar v bar and plus rho prime u prime v prime bar, right. So now we have a problem, right. If you recall earlier in the incompressible flow, we had most of the terms got cancelled out because rho was a constant, and your rho u bar v bar was nothing but rho u v bar, okay, rho u bar v bar and plus rho u prime v prime bar. That was the only thing that we had in the compressible flow, okay. In the incompressible flow we have got 5 terms, okay, and not only that, we have got now an energy equation. So if you try to derive using this averaging process, it will become very tedious, very cumbersome, and even to model the terms will be very hard. In fact, the number of unknowns will be much higher in this particular case compared to what we had in the incompressible flow, right. But there is a way out, okay. and that way out was basically suggested by Favre, and this is called the density weighted time averaging. Okay, we are doing the time averaging, but now we are weighing it based on the density, right. So, what we are going to see that now we know in the compressible flow that rho is also varying, right. So, somehow if you can put that rho, I mean variation in rho in one of the averaging inside, then it can basically we can reduce the number of terms in the averaging, right, especially in the multiplication of multiple variables, right. So, that is what exactly happens. So, what we can derive. So, now we will, instead of using the bar which was the Reynolds averaging, okay, we will use Favre averaging and we will denote it by tilde. Okay, this is the Favre averaging. And how do you define it? We will define it as given here, that we will divide it by 1 by rho bar and we will multiply the rho t. Okay. So, rho and whatever variable you have. Okay. So, rho multiply by whatever variable. So, if you have f variable is given for you, if you have variable f. So, basically you keep on multiplying rho f, take an average of that, divide by the mean of rho and call it as f tilde. Okay. The f can be anything, it can be your velocity, it can be your temperature, right. So, this is how we will derive your Favre averaging. So, what we are trying to do is we are basically trying to absorb the variation in rho into this rho f term. Okay. So, that you do not have to basically I mean we will see the advantage in the next slide. Okay. So, you can write it as rho f bar is equal to rho bar f tilde, right. If it is a velocity, you can write it as rho u bar is equal to rho bar u tilde. Okay. Now, let us work out the same thing that we had earlier, which is basically we want to do this rho u v, right, and we are going to use u equal to u bar plus u double prime. So, now you see earlier we had u equal to u bar plus u prime. This was the Reynolds averaging, time averaging, and this is the fluctuation. Okay, now our decomposition is different, it is the Favre decomposition. So, now we are saying that okay, no, instead of using this we are going to use u equal to u tilde plus u double prime. So, this is the fluctuation. So, basically if you have let us say a flow something going like this. Okay, so, I am saying that okay, my Favre averaging is defined something like this. Okay, this is my Favre averaging which can be different from the Reynolds averaging. So, take that Favre averaging out. Okay, this is my u tilde and whatever is remaining is your whatever was remaining earlier. Okay, this is your u double prime. Okay. So, this is the fluctuations after taking the Favre averaging, right. So, now work that out. Okay, rho u v. So, you can call it rho u tilde plus u double prime, v is v tilde plus v double prime, right. So, this is rho u tilde v tilde plus rho u double prime u prime v tilde and plus rho. Okay, so I have taken these two term, I have taken these two term. Okay, now I have to multiply that one. So, rho u tilde v double prime and plus rho u double prime and v double prime, right. So, these are the only 4 terms. Remember, I have not done the decomposition for rho here, right. Now, you take a mean of it, take average on both sides. Okay. This will become rho u v bar, right, and we are putting the average of all of this. Okay. So, what will happen now? Okay. So, we have basically rho u tilde v tilde bar plus rho u double prime v tilde bar plus rho u tilde v double prime bar and plus rho u double prime v double prime bar, right. Now, let us look at the some of the properties. So, now we have these 4 terms and let us look at some of the properties of the Favre averaging, right. So, this we have already seen, this is by definition that you have rho u bar is equal to rho tilde rho bar u tilde, right. Now, since u is equal to u tilde plus u double prime. So, you can what you can do is you can take this rho u equal to rho u tilde and plus u double prime rho double prime, okay, and take an average on both the sides, right. So, this will become rho u bar, okay, and this is also nothing but rho u bar, okay, because if you recall the definition, okay, rho u bar is equal to rho bar u tilde, right. So, you can write it as rho u bar. So, this is rho bar u tilde, this is again a coefficient. So, u tilde bar is equal to u tilde here, right. This is rho u bar and this is now rho u double prime. So, by this you will see that rho u double prime is 0, right. Remember rho u double prime bar is 0. So, the time averaging of rho u double prime is 0, the u double prime bar is not 0, okay. The time averaging of the fluctuating field extracted after the Favre average quantity is not 0, okay. On the other hand, if you do this u double prime tilde, that will go to 0, okay. That is again by the definition, right. You have this, okay, and take the Favre averaging both the sides. So, that will make the u double prime tilde is equal to 0, right. And u prime u double prime v double prime tilde is not equal to 0 obviously, okay, bar is not equal to 0, okay. So, now use these properties here, okay. So, you can see that this is v tilde, you can take that out, okay. This is v tilde rho u prime double prime bar, right, and similarly you can take that out as u tilde rho v double prime bar, and this you can write it as either u rho bar u tilde v tilde, you can write it like this, okay, and then it will become rho u double prime v double prime bar, right. So, this term will go to 0 and this term will go to 0, right. So, what you have is basically rho bar u tilde v tilde plus rho u prime v prime bar, right. So, now you see that we are back to business, because now we could reduce our term which the nonlinear term that appears in the momentum equation into the just two terms, okay, rho bar u tilde v tilde and rho u double prime v double prime bar, right. So, now it is very close to that what we had in the incoming momentum equation. We can use this relation and get our derivable RANS equations for the momentum as well as RANS equation for the energy. So, we will do that in the next class. Thank you very much.